Okay, how are we all doing? This is Mike Johnston here, and in this video, we are going to discuss an example on how to rapidly qualify and describe each one of these values that are given. And this was something that, as I've said before, I've battled with growing up through high school and even through my first couple of years of college, where I was never very good at naming. I always felt this was more of the definitions of the English portion of math course, and I never found any use for it until I had to later on go into advanced mathematics and physics and understand that there was a difference between a whole number and a natural number, and between an integer and an imaginary value, and that was how different theories were described. So I became a much better expert at understanding how to rapidly differentiate between all those values. So now I'm going to show you how I go through and do this. In the meantime, if you want to go ahead and pause this video now and try to work this out on your own and see how you do, you are more than welcome to do that. And that way you can check your work and compare it to mine. And you can also make sure that I'm right as well, because I'm known to make a few mistakes here and there. But go through and just try pausing it and briefly describe these values as being real, imaginary, rational, irrational, integer, wholes, and or natural values. So you're going to see that some will have more than one of those qualifications. Some will have many more than one of those qualifications. So you can go ahead and try that now in the next 30 seconds. So hopefully you're back now, and you've practiced this, and I will show you what I do. So before I go through and do this, I often draw myself my little number chart, my little number process flow chart. And I don't use a very large field. I use a smaller field, and it helps me break it down pretty rapidly. So I know numbers can be broken out into imaginaries. I'm just going to abbreviate this as imag, imaginaries versus real. I'm going to use my abbreviation for real. And then I know once an imaginary number has been qualified, it's done. It can no longer be further subqualified. Right? Real numbers can be broken down into rationals and irrationals. So I'm going to write IRR for irrationals and RATIL, I'll say ratio or rational. You could even write the whole thing out if you wanted to, but I'm just going to say ratio, rational, same exact thing. And then if an irrational number's been described, it can no longer further be subqualified. Rational values can be broken down further into integers, which I'm going to abbreviate as integers. And some may see the abbreviation written in this form with the funny Z with the extra little line through it. Let me do that better. It's a little bit tough for me to write this little Z, but some may see that abbreviation like such. So it looks like the integer abbreviation is like this. So it has the extra little Z line through it. I actually write it INT. I'm not very good at drawing that Z. Anyways, back to the process flow diagram. Integers can be further qualified as whole numbers, and then whole numbers can be further qualified as naturals. So I just did this process flow chart. Notice it took me about a minute. After you do it a couple times, it'll be even faster. So for me, it is often easier to recognize the difference between the dichotomy of real and imaginaries continuously. Instead of having to work vertically down from number all the way to n for each independent number, I like to go through and look at every single term and say, okay, is this real? Is this imaginary? Is this real? Is this imaginary? Is this real? Is this imaginary? So let's go ahead and try that out. So when I look at 2.43, so right now we're looking at 2.43, is this number real or imaginary? Hopefully we recognize this number is real. So I'm going to write the real term underneath of the abbreviation. -7, real. 2/3, real. 3 pi over 2, even though it has pi in it, it's still real. Negative pi has pi and it's still real. 0.0168, it is real as well. Square root of -3. Square root of -3. Remember, we defined an imaginary term as that I value, or the square root of -1, or any radical that has any square root that has a negative underneath in the radicand. So this guy actually is an imaginary value. So imaginary value. So he is imaginary. He cannot be further subqualified. So I'm going to put a little star underneath or above him just to make sure I know that I cannot further qualify him any further. He is done. So now when I look at negative square root of 3, negative square root of 3, the negative's out in front, that's okay. Negative being out in front is okay, very different than the negative inside the radical. So this guy is in fact real. 0 is still real, and so is 17. So as we said before in these videos, that most of these values that we're going to be working with in this class are in fact real values. So now I have my real versus my imaginary decisions checked off. So now I recognize that when I work through my process flow chart, I now have to make the decision between these values being rational or irrational. So rational or irrational. So I'm going to work my way starting left to right, recognizing whether or not 2.43, -7, 2/3, etc. are rational or irrational. So 2.43, can this be written as a fraction? Absolutely. So this guy is rational. -7, I'm just going to write RAT to abbreviate it. So -7 is rational. 2/3 is by itself, looked like a proper fraction, so it's rational. 3 pi over 2. 3 pi over 2. Remember, pi is a value that goes on to infinity. So any value that has pi in it will always be irrational. So I'm just going to write IRR describing that this value is irrational. 3.14 goes on forever and ever and ever and ever, never stops. Since it never stops, we can never actually write this as a fraction, therefore it will be irrational. So I'm going to put a little star above this, indicating that I can no longer further subqualify this. Negative pi, doesn't matter if it's positive or negative. If it has pi in it, it will always be irrational. And again, I'm going to indicate that I can no longer further subqualify this value by putting a star above it. 0.0168, we could definitely write that as a fraction. Definitely write that as a fraction. So we're going to put that as rational. I can no longer further subqualify square root of -3 because it's imaginary. And then if we continue on, negative square root of 3. Negative square root of 3 is the radical, the square root of a non-perfect square. Therefore, this number would never end. It is an infinitely ongoing value. So this value is also irrational as well. So negative square root of 3 is real and he's irrational. So I'm going to indicate that I can no longer further subqualify him by writing that star above him in that fashion. When I look at 0, 0 is in fact a real value. 0 is definitely, it is a rational value. We can go ahead and say that he is rational because he is written as a fraction forever, and so is 17. Those are rationals as well. So we have finished describing 4 out of the original set of values. 3 pi over 2 is done, negative pi is done, square root of -3 is done, and negative square root of 3. These guys are done. So I've indicated that in blue that that's where they stop. That's where they terminate in terms of our process flow diagram. So now we have the opportunity to qualify rational values as integers. But remember, not all rationals are integers. Integers have no fractional additives. They are nice looking values. So if we look at our integers, 2.43, is this guy an integer? Absolutely not. 2.43 has that 43/100ths of a decimal addition to that value of 2. 2 by itself is an integer, however 2.43 is not. -7 is in fact an integer, so we are going to write that as such. 2/3, again, fraction by itself. And when I say the term fraction, I realize that I know all values. -7 can in fact be written as fractions, -7 or 1. However, that's just something that I use to quickly indicate that 2/3 is in fact a rational value. However, he is not integer. 0.0168, this guy is definitely not an integer. 0 is in fact an integer, and 17 is in fact an integer. Remember, we described the integers as just a quick review. Maybe I should have done this at the beginning. Integers in that set notation, like such. So I could have drawn that better. Actually, let me draw that better. Let me draw that better so we can see that. That was really bad handwriting. So we would have, I did that a little too fast, -3, -2, -1, 0, 1, 2, 3. So remember, they have to follow this pattern. And if they do not follow this pattern, they are not integers. So now we have to look at whole numbers. So integers can be described as whole numbers. However, not all whole numbers are integers. So looking at -7, -7, is that a whole? Let's think. Whole numbers are the set of integers starting from 0 going on to positive infinity. -7 is negative, so -7 falls in fact down here. Therefore, he is not a whole value. So -7 is not whole, he is done. If we look at 0, 0 is in fact, 0 is in fact, I should have written this in red. So I should have written these in red. I'll just overwrite them in red. They are not, they're not ending. But 0 is in fact a whole number, so I'm going to write whole underneath here, and so is 17. So now, since we have finished our whole values, now we have to go down and look at naturals. And remember how we describe naturals. Naturals are a subset of both wholes and integers, but they do not include 0. They do not include 0. So if we look at this guy 0 is in fact he is not a natural value. He is terminated at whole, so he is no longer further qualified afterwards. 17, however, is considered a natural value. 17 is a natural value. So we realize that the only number that is real, that is rational, that is an integer, that is whole, and is natural is in fact 17. Most of our values are just real and rational. We see -7 is real, rational, and is an integer. 2/3 is real and rational. 3π/2 is real and irrational. -π, real and irrational. 0.0168, real and rational. Square root of -3 is imaginary, and the negative square root of 3 is real and irrational. So this process tends to help me think it through a little bit better than trying to go through 2.43, for example, and say, okay, is this guy real or imaginary? Okay, he's real. Let me continue on. Is he rational or irrational? Oh, he's rational. Let me continue on. For me, it helps to work through this entire group, working through my process flow chart from top to end.